Welcome back to Video Assist. We're hoping you find these videos useful. We're looking at the incline today. Unit 1, Section C, Activity 5 deals with the incline. First of all, we'll look at the case with no friction. With no friction, there's only two forces. The force of gravity acting straight down and the normal force acting at 90 degrees to the surface. It's handy to know that this angle in here, if we draw this straight down at 90 degrees, this angle in here is also equal to angle theta. Geometry tells us that those two angles, this angle and this angle, are always equal. Something you have to remember for the incline. Well, to begin the problem, we've got our free body diagram drawn. We have to identify the direction of the acceleration, which is down the incline. We always consider that the direction of the acceleration will also be the positive direction. Both are marked here. Begin with Newton's second law, which says F net equals ma. This rule says that if you add up all the forces in the direction of the acceleration, that equals the mass times the acceleration. Well, which forces act in the direction of the acceleration? Fn does not. Fn is perpendicular to the acceleration. It has no component in the direction of the acceleration, so we can just forget about Fn. But Fg does have a component along the direction of the acceleration. I'll draw it in here, dotted. That component of Fg pulls the mass down the incline and causes it to accelerate. What is the size of that component? Well, that would be Fg sine theta, because it's not adjacent or beside the theta. Therefore, we'll use sine theta. Fg sine theta equals ma. We'll replace Fg by mg, and we've got our equation. And notice that since we have m on each side, we can cancel it out. So mass has no effect on the acceleration if there's no friction. Let's leave that and look at the case with friction. Let's suppose that we have a frictional value of mu. Its component is mu. Again, we have to draw the free body diagram. Well, again, force of gravity is straight down. The normal force is still at 90 degrees. But there's one other force, that is the force of friction acting straight back. Identify the direction of the acceleration. That'll be down the incline, like this, and we're also going to assume that that is a positive direction. Well, which forces have an effect on the direction of the acceleration? Well, Ff obviously does, because it's parallel to the acceleration. The normal force does not, because it's perpendicular. It has no component in the direction of the acceleration. But Fg also has a component, as before, in the direction of the acceleration, and I'll draw it in here again. That component there is in the direction of the acceleration. So we have two forces that we're dealing with that have a component or in the direction of the acceleration or opposite the direction of the acceleration. Well, let's substitute that into Newton's second law, which is F net equals ma. And we will have this component here, which is away from this angle here, theta. Remember, that's theta. That component there is Fg sine theta equals, or must not forget, subtract the friction, because it is also there, equals ma. We'll replace the Fg by mg. Mg sine theta minus the force of friction equals ma. And that's as far as we can go with that particular equation. We have no values, in this case no numbers to substitute in, but we would work with that equation. However, if this was derived parallel to the acceleration, I'll write down parallel to a, there's another formula that can be developed or written perpendicular to a. Often you have to create a second equation on the incline. Well, what is the situation perpendicular to acceleration? In other words, the direction of the pin. If the acceleration is along here, then perpendicular to the acceleration, the forces are balanced. That is always true. Perpendicular to the acceleration, forces will be balanced. Well, what forces act in the direction of the pen here? Well, Fn obviously does, but Fg again has a component that acts in that direction, perpendicular to the acceleration. That component is beside the theta, so it's Fg cos theta. That has to equal, Fg cos theta has to equal the normal force. And we can write then mg cos theta equals the normal force. That's the second equation. There is even a third equation that we can create, but it doesn't come from the free body diagram. It comes from our notes that the force of friction is equal to the coefficient of friction, mu, which is normally always given, times the normal force. This is the third equation. So we have three equations which we will use to solve our incline problems which involve friction. Good luck.